so this is question 5 of the exercise sheet, huh? And I'm not going to write it down because it is already on the... Can the screen of the computer be turned off? It is... but I can say what it says in words. It says, take any bijective map from R2 to R2 that has the property that it preserves the collection of all lines in R2. And all the lines, not necessarily only the lines that go through the origin, but also just all the lines in R2, as also explained on the exercise sheet what I mean by a line. And the exercise was to show that such a bijection is an affine transformation. Okay? So let's... yeah, and I have now two blackboards, a whiteboard and a blackboard. So I want to use the whiteboard for geometry and drawing of lines, because lines have to play a role. And I will use the blackboard for writing text. So, solution of exercise 5. That's what we are going to do. And so we have to start with a map F, as in the exercise. That F from R2 to R2 be bijective, preserve lines. Let me also... lines. Okay, so we have such a map F, and we have to show it is an affine transformation. Well, so here, let me start to draw a little bit. In the plane R2, we have two coordinate axes, right? And we have some points that I want to point out. There is the point 0, 0. Is that big enough also? Can you read it, René? Yeah? We have the point 1, 0, and we have the point 0, 1, okay? And that is our... You usually use these points to put coordinates on a plane, right? You need an origin, and you need two directions. That is how you make a plane. So this is my basic start information for a plane. And I want to see what F does with these points, right? So... But, so then, F of 0, 0, F of 1, 0, F of 0, 1 are distinct. They are not equal because F is bijective, right? F cannot map different points to the same point. That's forbidden. F is bijective. And also, you see, these 3 points, they do not lie on one line, because there is only one line through the first 2 points, and this point is not on that line. So, okay, and F preserves lines, so are distinct and not on one line. But then, now. When was our exercise, our training session? 2 days ago? You still remember? What can we do when we have 3 points that are distinct and not all on one line? We have, yeah, we have exercise 2B. So exercise 2B gives a unique, actually, I don't think a unique G in the affine group such that, and now I want such that this G maps this point back to 0, 0, this point to 1, 0, and this point to 0, 1. So, and I can write that, so G composed F maps let me introduce fixes 0, 0, 1, 0, 0. Right? That is what we get by exercise 2b. So this, and I also say, and I'm not going to write, this G is affine, it preserves lines, right? An affine transformation does preserve lines. You see that from the way it is written. It sends a vector to ax plus b, and a translation preserves lines, and multiplication by a matrix also preserves lines. So that's okay. So this G composed F also preserves lines. And so what we have to show that F is a affine transformation is equivalent to showing that this one is an affine transformation. Because if G composed F is, say, an element H in the affine group, then F is G inverse composed H, right? And that is affine. So we can assume, and now we can assume, or say by replacing, let me say by replacing F with G composed F, that F fixes these 3 points. Right? So you see that the fact that in group elements are invertible is heavily used. Because we use that we can move things from one side to the other. If G composed F is H, then that's the same as F is G inverse composed H. And so we do that. So now I can try to do something, right? I move to the geometric side. And now, so my map F fixes these 3 points. So what intelligent thing can I do now? I can first conclude. Can you say it louder? Yeah, okay, good. You say I should look at what F does with this line, for example. But F fixes this point and F fixes that point. And this line is the unique line through these 2 points. And the image of F, the image under F of that line is also a line that goes through these 2 points. So F fixes this line, right? Maybe I first go to the, so then F fixes the line through 0, 0, and 1, 0, etc. Right? We can. So I draw. So the line that I have drawn is mapped to itself. Maybe not every point to itself. That is what I have to show. Actually, I have to show now that this. So by my reduction, if this G composed, this new F is affine, then it will be an affine thing that fixes these 3 points. But then it is very easy to see, actually also in exercise 2b, that the only affine transformation that fixes these 3 points is the identity. So we have to show that our F now, that fixes these 3 points and preserves lines, is the identity. And it maps this line to itself, it maps this line to itself, and also this line, right? Those lines are all mapped to themselves. But can we find more lines that are mapped to themselves? So here is the crucial step. This is the most important step, I think. So let us look at the vertical line through this point. It is the only line through this point that does not intersect this line because it is parallel to it, right? So my map F that preserves lines should send, it sends this line to itself, it sends this point to itself, so also this line goes to a line through this point, but it should go to a line through this point that doesn't intersect this one. So that must be the same line. Yeah? So that line is fixed, but for the same reason, this line is also fixed. Now, another simple idea is that this point now has to be fixed, right? So I win something. The point 1, 1 is also fixed. And now there is nobody stopping me, right? So I can also draw the line parallel. I haven't used this line yet, but now I have to play that card. I have to say, well, this line has a parallel line through this point, right? So here I go. And which points are these? This is the point 0, 2. This is the point 2, 0. And they are fixed. And you see that I can go on. Right? So what you see right away, if you make the picture bigger and bigger, if you continue drawing parallel lines in these 3 directions, then you see that F fixes all the points. So here if I were writing, so I should say look at the picture, but then F fixes all, or x comma y, with x and y in the integers, right? Because if I can get from 0 and 1 to 2, here you see I draw another vertical line, I get to 3 and so on. And I can probably also go to the left, yeah? I can maybe also draw this parallel line to that one through this point, and then I get a point here, right? So I hope you are convinced that I get this. But I can also divide. If I have the point 2, 0 here, for example, or what I could also do is intersect this line with this line. This point here in the middle is the point 1/2, 1/2. So I get also fractions. And there is nobody who, well, I can get arbitrary fractions as well. If I have the point, say, n, 1, and I draw the line, and I intersect it with this line, then here I get 1, 1 over n. So actually, we can make it better. And we could put q here, right? But q is not r. So if my question would have been about the field q instead of the real numbers, we would have finished already. But now there is a problem, right? So that is annoying. And how do we solve that problem? We solve it by generalizing the question and understanding better what is happening. So now we are stuck, unfortunately, and we have to unstuck ourselves, and so you have to broaden your view a bit. Let us consider, well, no, okay, no, I don't do that like that. I will do the generalization later. So we have to look at what happens with arbitrary x and y in the reals. So actually, I do a definition. Let sigma from R to R be the map, be defined by, I want that f of x, 0, so for all, that f of x, 0 f fixes this coordinate line, where the second coordinate is 0. So if I have an x, 0 on that line, it should go to another point on that line. Now I want to erase this. And that gives me a map from R to R that I call sigma. And we are going to we have to prove that this sigma is the identity map. So then maybe we better try to understand some properties of this map sigma. So here now I have this coordinate line, this coordinate line. Here is again the point 0, 0. Here is the point 1, 0. Here is the point x, 0. Okay? And here is the point 0, 1. And yeah, so I won't, so the claim I want to make, can you read this low? Yeah, so I claim, I will make the notation very short. Sigma is in the automorphism group of R. So I claim sigma is a field automorphism of R. Sigma of x plus y is sigma of x plus sigma of y, and sigma of x times y is sigma of x times sigma of y. And I'm going to draw pictures to prove it. So here is an x, and I suppose I also have a y. And now I want to prove that sigma of x plus y is something. So I have to make x plus y appear in this picture. So maybe I do that by taking, here I have this line joining these two, and I move this point to the other coordinate axis by taking the parallel line. Huh? These two lines are parallel, then this is the point 0, x, okay? And now I draw the horizontal line through this, and I take the vertical line through the oh, y, x, very good. I knew that the coordinates were right, but maybe not in the right order. Y, x, yeah, good. And now how do I get the sum? I take, again, the line parallel to this one through that point, right? So here I have, well, that is, op. So this is the line that is parallel to this. And here I have my point x plus y, 0, right? And I claim that this is already a proof that sigma of x plus y is sigma of x plus sigma of y, because if I would, if my whiteboard was twice as long, I would do this. I would say, well, f maps this whole thing to f is a bijection from R2 to R2 that preserves lines. So actually I will make the second one smaller, then it still fits. Okay, here I have my basis points. 0, 1, 1, 0 is fixed, 0, 1 is fixed. But where does x, 0 go? It goes to sigma x, 0. And my y goes to sigma of y, 0. I don't know what they are, but they are on that line. And the line that's through x, 0 and is parallel to this will go to this line. It goes to the line parallel to that line that was fixed, and it goes to 0, sigma x. And so this line parallel to that, this line here that I used goes to this line, and this line here through this point y, 0 goes to the vertical line through this point. And here I have the point sigma, now I do it right, sigma x, right? And now this last line that was also parallel to this line that was fixed, it goes here, and I see that this goes to sigma x plus sigma y, 0. Isn't that funny? but it also goes to the image of this point, and that one goes, so this one goes to sigma of x plus y comma 0, and these two are equal by my argument. Any objection? So we have done the addition, right? And then what is left? The multiplication. We also have to show that sigma of x times y is sigma of x times sigma of y. So yeah, I have to erase everything. Sorry. But it is recorded, right? So we can see it back. So I claim that you can also do multiplication using lines in the plane. And actually, maybe you even know that better than for addition. Yeah, so, okay. So here is again my line. I have 0, 0. I have 1, 0. I have 0, 1. And I take, say, an x, 0 here. And I want to multiply with a y. So I have a point y, 0. And now what do I do? With this line, oops, that is not really parallel. Maybe I should do a better. So it ends up here. It is parallel to this line, right? So this line here. This is the point 0, x. I take the horizontal line there. So the horizontal line and the vertical line here. So this is the point 1, x. And now the line that goes through that is the line through the origin with slope x, right? It is the line, well now unfortunately my x is called x, otherwise I would say y is this number times x, and that number is this x. Yeah, it is the line through the origin with slope x. Line with slope x through the origin. And so if I take the vertical line there, then here I have the point y, x times y, right? It's as simple as that. So now I have that. I can bring that to the vertical axis by taking the horizontal line, and then going back here, I get x, y, 0. And now I do f again, and you can figure out for yourself that I get, this gives sigma of x times y is sigma x times sigma y. So we are, has happened now? I think something very nice has happened. We started a bit with a very strange question about real numbers. But at some point, we saw that we had a map from R to R, and we wanted to see what properties it had. And this now, what does it show? Indeed, we have proved that it is an automorphism. But I also want to remark our arguments prove a very nice theorem. Very fields. Let F be a field. And F from F2 to F2, a bijection that preserves lines. Okay? That is. So what I do is I say, well, we have proved something actually for arbitrary fields, because we have only used addition and multiplication. So we never took a square root or anything. All the arguments are true. We never even divided by something that now could be 0, but in the rules were not 0. We never divided by 2 or so. We didn't do that. So then there is a unique, this is notation for there is a unique sigma in the automorphism group of F, and there is a unique G in the affine group of F2. So this one is given by maps of the form X goes to AX plus B with a 2x2 invertible matrix with coefficients in F, and the B is an element of F2, such that for all xy in F2, sigma of, the f of x of the point xy is the g of sigma x comma sigma y. I claim this is what we have proved. But to really do that, you have to go to write down all the arguments and check each time that it works for an arbitrary field. But this is the theorem that we should really write down and publish. Well, it has been published already, but, but this is something nice. I really like this. Let me put a frame around it. And then you could hang it on your wall as a for to see it every day. So, and maybe even it would be nice to show. So before we now finish this exercise 5, I want to point out another case, because now we have a theorem that is true for every field. What does it say for the simplest, for the smallest field that exists, right? The smallest field, how many elements does it have? 2? 2, eh? Yeah. So take F equal to F2. Then, what does it say? So now something very funny is happening, because how many points are there on a line if the field is F2? 2. So, but that means that all the lines in F2, the lines in F2 are all these subsets of 2 elements, right? I mean, on a line there are only 2 elements. The line in F2 times 2. Yeah, thank you. It would also be true in a higher dimensional F2 vector space, huh? Because a line is a one-dimensional F2 vector space, maybe translated away from the origin, but it has only 2 points. And so the notion of points lying on the same line over F2 is a bit silly notion, because for every 2 points there is a unique line that goes through it, and there are no other points on that line. So, so what does our theorem say? Our theorem, and yeah, also how many automorphisms does this field have? No, one only the identity, right? So the theorem says that the set of these f's, so the f's that I consider that preserve lines, are the f set of f from f2 to f2 squared that preserve lines and are bijective. I almost leave it out. That set is the set sim f2 squared, right? All the bijections are okay. And how many of these are there? How many elements does this set have? 4. And so here, if I take all the permutations? 4. I want the result as a number. 24, right? Okay, but This is the group with elements. And the A is in. Yeah. So and actually, if you look at the. So this now gives a group homomorphism surjective to the GL2 of F2. Because you send a B, comma A to A. And this group, how many elements does it have? I think you did that in my exercise sheet also. For any prime P, you had, so this has, if you compute it, this has 3 elements. Actually, the 2 by 2 matrices, if you look at this F2 squared, there is the origin that will be fixed by all these elements linear maps. And actually, there are only 3 other elements in it, 1, 0, 0, 1, and 1, 1. And this group, you can check, mutes them just as the group S3 does. So these are, why do I write 3? These are, this has order, or, well, actually, let me write it correctly. This is the same as the sim of F2 squared, but I remove the 0, 0. So then I have a set of 3 elements, and I say GL2F, the way it acts on F2 squared, gives all the permutations of these 3 points. So, and now I want to make a link to the Galway Theory course, because there you saw how to solve equations of degree 3, and I claim that this tells you how to solve equations of degree 4, because this is the group of permutations of 4 things, and it maps surjectively. It has a quotient that only permutes 3 things. So if you can, so actually I don't need to explain that. My colleague who teaches the, Peter Steven, and who teaches the Galway Theory course, so we will say, so now we can solve, he will do it, right? Or you do it in an exercise, solve equations of degree 4. And I can tell you how it will go. The kernel of this homomorphism of groups, that is the translation of the B comma ones, right? They are the ones B comma identity go to the identity. So actually, this picture in group land says that if you solve an equation of degree 4, first you will solve an equation of degree 3, and then you will solve 2 equations of degree 2. That's what it says. And this will be explained. Okay, so now we can go back to the real numbers. So let me do that here. I have 5 minutes for that. Actually, maybe, okay, good. So I actually have an idea to prove still. For every, well, actually, for every sigma in the automorphism group of the real numbers, sigma is the identity of the real numbers. And actually, I will do that. You will prove it in an exercise sheet. Yeah, I think that is a good thing to do. Exercise for later, next training session. Because then now I can spend a few minutes. I have still 5 minutes, I think, huh? Or do I have 15 minutes? Oh, okay. Well, what do you want? That I do it, or that you do it herself or herself? There's almost nobody. Would all be enthusiastic. I say, oh, I want to do that myself. But not yet. Okay, so you want me to do it. Who wants me to do it? Well, that's even less. So you want nothing. Let me ask again. Who wants me to do it? It's okay to say that. But do you want to do it yourself then? Okay. Then I try to clean this blackboard a bit. So the official, I think in the planning, if you look at what I was going to do in this lecture, was Klein's program. And Klein is Felix Klein. He was a professor in Germany in the 19th century. I think he gave his inaugural lecture in 1872. For some reason, this is stuck in my memory. And he gave a lecture on relations between groups of transformations and geometry. And so I want to, now my lecture becomes a bit vague, but the examples will be concrete. I think this should still dry. Well, okay, geometric structures on R2. We can look at the set of that, whatever we mean by that. But for example, think of the collection of lines, right? That is the example that we did. So he says this is related somehow to groups, subgroups. It is almost like a Galois correspondence. Subgroups of sim of R2, just like what we did with the lines. So how do you do that? How do you, if you have some geometric structure on that, you would say, well, I take automatism. Suppose I have a vector space structure, R vector space structure, and I take its automorphisms, then what do I get? Here, I get the group GL2R, right? The linear invertible transformations. This corresponds to that one. And we have proved that if you take permutations of R2 that preserve the collection of lines, then what did we get? What did we get? Affine group of R2, right? Right? That is the theorem that you will do the last step of, yeah? And actually, yeah, so if you can go one way, maybe we want to have one more. If I say R vector space structure, so I want to go back in time. People always talk about Euclidean geometry, right? So actually, I don't want to have R vector space structure. Euclid was a few hundred years before Christ, probably, minus so many hundred. And so what, actually, sometimes it's easier to start here, but here we say, okay, distance. We know what the distance between 2 points in the plane is, right? With the theorem of Pythagoras, you can take, if you have a, yeah, the difference of the x coordinates squared plus the difference of the y coordinates squared, and then you take the square root of that. That's the distance. If you take permutations of R2 that fix the distance, what do we get as a group? The i's, right? Yeah. So we can say we get isom R2, and maybe how do you describe these? Okay, this is the set of maps. X goes to AX plus B, right? Where the B is in R2. The translations, you can do all of them, but the A is orthogonal, right? A transpose times A group, right? So who has another example that we would like to talk about? Or I think that if you observe distance, then it is a nice exercise. Maybe I shall also put that on my exercise sheet if there is time for. If you preserve distance, it is a lot easier. Here, this was difficult. We had to do something really bizarre. We had to prove that the automorphisms of R are all the identity. For these cases, this is easy, actually, relative to that. What else can we do? We can say, well, what if we want to have here this group? This A is in the group that is called of two matrices. It is contained, it consists of rotations and reflections, right? Reflections about a line through the origin and rotations over some angle. And the reflections have determinant -1. So the rotations, yeah, so this has the map determinant goes to the set 1, -1. The determinant of such a thing can be 1 or -1. And so that means that this group has a subgroup, namely those of determinant 1, and that's the rotations. So sometimes you want to go back. And here is an example of where we have an interesting subgroup and we want to know what kind of geometry it corresponds to. isom R2 plus. And what is that? This corresponds to the ax plus b with a in what is called f. Term orthogonal and determinant 1, and the b should just be in R2. Okay, so what does that correspond to? What kind of thing should we have there? What do these, so the question is, what is it exactly that these transformations preserve? So they do preserve distance, that I know, because then I get this bigger group. So I should ask a little bit more. Orientation, thank you. And if you don't know what an orientation is, then Klein would say, but you see it in the group. And the rest is your problem. So maybe I give one more example. Suppose here we do angles. And maybe when I say angle, should I make more precise what I mean, or is it okay like this? Hmm?
More precise.
You need more precise, and why?
To agree on the term.
But no, but I think there are two possible terms that I could mean. I could mean an angle that has a sign, plus 20 degrees or minus 20 degrees, or an angle that has no sign. So if you do Euclidean geometry without orientation, then you have only angles up to sine. So if you have a plane with no given orientation and I have two lines through a point, then I cannot say if the angle between them is plus something or minus something. It's because you don't know how you rotate from one to the other. So if I really want an angle, not only angle up to sine, what is the group then, right? That is maybe an interesting question. If I have to preserve angles, but I can change the sign of an angle. So, for example, a symmetry will change the sign of the angles, right? So up to sine, it preserves it. But what other kind of maps preserve the angles up to sine? Well, translations, they preserve everything normally. So we have the translations. What? Rotations. Yes, rotations are good. But I think if I have already the symmetries, I also have the rotations. So that doesn't make it bigger. I need something bigger, because if I do only translations and orthogonal things, then I end up with the distance and that group. But I think there are angle preserving maps that do not preserve distance. Like what? If I zoom in, yeah, so zooming is the right word. If I make everything twice as large, or so scaling, right? So this is a group where you can not write it, but it is generated by translations, rotations, one symmetry. Well, I have to take at least one symmetry because it is up to sign that we want, and scaling. Scaling any positive or negative real number, non-zero. Dilations, yeah. But the same in the two directions, right? So you get matrices, say maybe of the form lambda 0, 0 lambda times A, and A is in the O2, this is horrible, O2 of R. And the translations, of course. And now my blackboard is full and I should stop. Okay, thank you.